Section 14.3, buffering capacity. The amount of protons or hydroxide ions in the buffer can absorb without a significant change in pH is the buffering capacity. So it's this ratio that determines our pH. And when we use up all of this, or we use up all of this, we have broken our buffer. Right? Buffers with a large capacity contain large concentrations of the buffering components, and this value up here would be very large, and so we can absorb a lot of acid. And if this HA has a very high concentration, we've got a very high concentration of our conjugate weak acid, then it can absorb a lot of hydroxide ions without breaking our buffer. The pH is going to be determined by the magnitudes of that ratio. We're going to calculate the change in H+ that occurs when 0.01 moles of gaseous HCl is added to 1 liter of each of the following solutions. Either a 0.5 molar acetic acid and acetate solution, or a solution of 0.05 molar acetic acid and acetate solution. For acetic acid, our Ka is 1.75 times 10 to the minus 5. For both solutions, the initial pH can be determined by using the Henderson-Hasselbalch equation. We've got pH is pKa plus the log of AHA, a ratio of our conjugate base to our conjugate acid. In each case, they're both equal to each other, so we're going to have something like 0.5 over 0.5, and that means we've got a log of 1, and the log of 1 is equal to 0, so our pH is equal to pKa, and this is a very special spot where they're equal to each other. So our pH in both cases is going to be 4.74. So they're both starting out at 4.74. Now we're going to add HCl to each of these solutions as the major species before any reaction occurs. So we've got our HA, we've got sodium, which doesn't do anything. We've got some A-, we've got some H+ and Cl-. Now the Cl- isn't going to do anything. And our water. Since we have a relatively large quantity of H+, it's readily going to react with any of our effective base. Cl is not going to form HCl. So our conjugate acid, or conjugate base, A-, is going to react with our H+ to back form our conjugate weak acid. So H+ will react with acetate to form acetic acid. Right? How much are we going to form of our weak acid, and how much are we going to lose of our weak base is going to affect that pH, because remember our pH is going to be pKa plus the log of AHA. And adding in H+ is going to drop our A- concentration and increase our HA concentration. Because it is a weak acid, we're going to assume that the reaction runs to completion, that the strong acid is going to beat up all of the weak base and turn it back into our conjugate weak acid. Our 0.01 moles of added H+ will convert 0.01 moles of our acetate into 1.01 moles of acetic acid. For solution A, since the volume is in 1 liter, the number of moles is going to equal the molarity. And the following calculations will apply. So before the reaction, we had 0.01 moles of H+. We had 5 molar acetate. And we had 5 molar acetic acid. After the reaction, we've allowed this in our stoichiometry step to convert some of our acetate. Right, we're going to lose some of that acetate. It's a reactant. And then we're going to gain some of our HA. Now we can plug that back into our Henderson-Hasselbalch equation. So originally we had 0.05 divided by 0.05. We're going to add some H+. And now we're going to have 0.04 over 0.06. So our new solution has a ratio of 0.67 when we started off with 0.1. So plugging that back in, we're going to end up with a pH of 4.74, and there's really been no change, right? I think it comes out as like 4.7, 0.38 or something like that. It's really no change in our pH. All right, for solution B, we're going to do the same calculations. So we're going to do a stoichiometry step. All right, we're starting off with 0.01 before of our H+. We got 0.05 of our acetate, and we've got 0.05 of our acetic acid. We're going to consume some of our acetate. This guy's going to go down by 0.01. This guy's going to go up by 0.01. So that when we look at our new ratio, we started off with 1. Now we've got 0.04 over 0.06. And our ratio becomes 0.67. So although a pH change is going to happen, it's still small, but it's a lot more than it was compared to A, right? And if we break that buffer, so we added, let's say we added in 0.06 molar H+, right? We got a number bigger than this, and if you end up with a negative number either on the top or a negative number on the bottom, then you're just going to have to treat it either as a strong acid or a strong base problem, right? So here's what you're going to do. In solution A, we had about a 2% change, and in solution B, we had about a 50.5% change. So solution A, which has a larger quantity of the buffering components, has a much higher buffering capacity than solution B. Optimal buffering occurs when our HA concentration is equal to our A- concentration. So that means it's got the biggest range to go in either direction. This ratio is going to start out as to 1, and it's going to be most resistant to changes from either addition of strong acid or strong base. The pKa of the weak acid to be used in the buffer solutions to be as close as possible to the desired pH. So when you're making up a buffer, one of the things that you're going to want to do is look and see where is the pH that you want to be. So if you're looking at physiological pH, right? So we want our bodies to be somewhere around pH of 7, right? We want to pick a something that's got a pKa. So I would have done a table here that's got pKa's, right? If I need a solution that's going to be buffered at 4.3 and I can choose from these acids and their sodium salts, which ones do I want? Well, we're going to calculate the ratio of HA to A- required to yield a pH of 4. Which one is going to work best? Well, our pH of 4.3 is going to correspond to an H+ concentration of 10 to the minus 4.3, or 5 times 10 to the minus 5. So we're going to look for a Ka value. Since Ka values rather than pK values are given for the various acids, we'll use this formula. Honestly, I would have just done it all as Kas and then compared it. Right? So we're going to use that equation, and we're going to want the one that's going to give us the Ka that's close enough where this ratio of 1 will be. So if I look at my ratio of HA, that's going to give us this concentration of H+. Right? We're going to substitute in the H+ and the Ka for each acid to calculate the ratio needed in each case. So we'll end up with 3.7 times 10 to the minus 2 for chloroacetic. And then down at hypochlorous, we're going to get 1.4 times 10 to the plus 3. Right? We've got these two guys that are kind of in the middle. And since the benzoic acid is the one that is closest to 1, the system of benzoic acid and its sodium salt will be the best choice among those given to give you a buffering solution at a pH of 4.3. The optimal buffering system has a pKa value close to the desired pH, and the pKa value for benzoic acid is 4.19. So looking at this pKa value and the target pH, we know that our ratio is going to have to be a little bit more towards the A- side rather than the H+. So we're going to want something that's a little bit bigger than 1.